Question number 2, we have sulfuric acid. So we know that it's manufactured by contact process, one of the very important reactions involving at least, only one of the steps is actually reversible, and that happened to be a very popular equilibria question as part of physical chemistry. Anyway, what do they want us to do here? They want us to write an equation for the reaction between galena. So galena is actually PBS according to this question. So this thing is reacting with oxygen. So oxygen in the air, oxygen molecule, I guess. And then you're gonna form sulfur dioxide. Di there refers to times 2 oxygen. And you're gonna get lead 2 oxide, where you have Pb2 plus and O2 minus. As you can see, the charges cancel out. You just need one of each there. So it's PbO, lead 2 oxide, because you can also have lead 4 oxide, where you have Pb4 plus, and the formula will be PbO2. Well, balancing the equations, you will see straight away that this equation is not balanced because 2 oxygen plus 1 oxygen is 3 oxygen. You have 3 oxygen atoms there. You need 3 oxygen atoms. Start to use fraction. So 3 over 2 is the best one to use because 3 over 2 times 2 oxygen in one molecule, 3 over 2 fraction in front, you get 3 oxygen atoms on the left-hand side. However, some people really don't want to use fractions, despite having done fractions in chemical energetics as part of AS level physical chemistry. You know that the use of fractions is acceptable because, it is after all a symbolic representation. That's what chemical equation is all over. So you could multiply by 2, you could get 2, 3, 2, and 2. They will also be balanced. It's just 2 times multiple. Anyway, the next bit, identify oxidation number, but be careful, they want the changes. Changes means from something to something. So make sure you specify that. Okay, we know we started from lead 2. We need to work out lead 2 oxide formation from lead 2 sulfide. So this thing is called lead 2 sulfide. IDE because it's S2 minus, Pb2 plus, S2 minus. So we can see that there is no change in the oxidation number of the lead there at all. But we know that oxygen from 0 in O2 to minus 2 in SO2 and also PbO. So the change there is from this to this, or you can say minus 2 minus 0, the change is minus 2 there. In terms of the sulfur, is there any changes in the sulfur? There are no changes in the sulfur there is a change in the sulfur. So we know it's Pb2 plus S2 minus. So that is from minus 2 in PBS. Your ionic compound contains the S2 minus. The oxidation number of the species is the charge of the ion. So it's minus 2 in PBS. Now you have SO2. SO2, the sulfur is bonded to something more electronegative than itself. So you got 2 oxygens. The oxygen is going to be the one that carry the minus 2 there because the oxygen is more electronegative than sulfur. Electronegativity, AS level concept, the ability or the power of that atom to attract the bonding electrons towards itself, leaving the sulfur with a positive oxidation number. Overall, the oxidation number of this compound, of this molecule is 0, and that is part of the rules of oxidation number there. So it goes to plus 4 in SO2. The oxygen, so this is referring to the oxygen, so that's why it's minus 2 in SO2, but the sulfur is plus 4 in SO2 there. So the change is going to be plus 4 minus minus 2. If you think about it, plus 4 is the final one, minus minus 2, that is plus 4 plus 2. You get an increase of 6 oxidation number. Okay, hopefully that makes sense to you. Now the next bit is basically about this equilibria. As I did mention, there is one step in the contact process. Somewhere along the way to produce your H2SO4 sulfuric acid, you need to go through this main-mate equilibria process, reversible reaction there. So state the temperature usually chosen. So typically it's around 400 degrees Celsius or 500 degrees Celsius. Around 400 to 500 would be alright. If you want to be safe, you can write 450, but I think 400, 500 degrees Celsius will have been alright as well. But they did say the temperature, so you shouldn't give a temperature range. You shouldn't give 400 to 500 degrees Celsius, but really, they would have been acceptable as well. I imagine that. Now explain this in terms of reaction rate and also Le Chatelier principle. Le Chatelier principle basically says that when a system is in equilibrium and you introduce a change to the system in equilibrium, the equilibrium will try to oppose the change in order to go back to equilibrium. So it's basically like push and pull. It's basically like homeostasis in biology. It's basically yin and yang, just like in physics, forces, push and pull, that kind of stuff, reaction and action forces, Newton's third law. Reaction rate is how fast is the reaction going. Le Chatelier principle is to do with equilibrium, is to do with how much. How fast versus how much is often something that is asked in this idea called rate versus equilibrium, and it happens to be one of those things that are always asked together because students always get them confused, and examiners love to ask this again and again and again. You get 1 mark here in terms of this temperature. So high temperature is required. In fact, high temperature favors faster rate of reactions. It will make the reaction rate faster or higher. Reaction rate higher or faster. They did say explain, right? So you got to talk about Le Chatelier principle. Boltzmann distribution. What am I talking about? Okay, so molecules or particles. Molecules will have greater kinetic energy, and your whole Boltzmann distribution would actually shift to the right hand side, and therefore there are greater proportion of molecules with enough energy greater than or equal to EA, therefore rate is higher. Okay, so in terms of the equilibrium, however, the forward reaction is exothermic. If you look at the enthalpy change, is negative there. So the forward reaction is exothermic. We're going to talk about Le Chatelier principle. As temperature increases, the equilibrium or the system which is the equilibrium, so it doesn't matter, you want to use equilibrium or the system, will try to oppose the change. It will try to decrease temperature. All right, so how would you decrease the temperature? All you know is you just know how to release heat, and that's why we stated the first statement, the forward reaction is exothermic, it releases heat. When we increase temperature, the system wants to try to oppose it to decrease the temperature. So you will still release heat because that's all you know, but you will release less heat. And when you release less heat, you're going to favor the backward side, because when you favor the forward reaction, it will release more heat. To release less heat, you will favor to the left-hand side. So therefore, equilibrium shift to the left and explain blah blah blah, and therefore it will favor backward reaction. So in terms of the yield of SO3 will decrease. So we get lesser SO3 in this equilibrium as temperature increases. So really 450 degrees Celsius is really a compromise between you wanting a low temperature versus the reaction not going too slow. So this is a compromise temperature where the equilibrium yield of SO3 is acceptable enough at this high temperature, given that the rate is not too slow, such that you have a productive day in the industry, not having to wait for your products for such a long time. Anyway, the next question really is about stating and explaining as well in terms of the pressure conditions. Now, in terms of these conditions, why these conditions are not actually used. So from your syllabus, you will know that we use 1 atmospheric pressure. So unlike the Haber process, where you actually have to go to like 200 or 300 atmospheric pressure to have an appreciable equilibrium yield of that ammonia, here 1 atmospheric pressure, you already get good enough yield of SO3. So despite the 3 moles of gases, 2 mole of gas plus 1 mole of gas, 3 moles of gas on the left and 2 moles of gas on the right, despite the 1 atmospheric pressure, it is good enough to actually produce a high enough yield of SO3. So we apply and use 1 atmospheric pressure. That is your condition. So in terms of rate, so higher pressure is good because Higher pressure means the reacting particles or the reacting molecules are squeezed much closer together, and therefore in terms of collision frequency, they will collide more frequently, and when they collide more frequently, the rate is faster, so the rate of reaction is faster. Okay, however, in terms of equilibrium, in terms of equilibrium or equilibrium, it's basically Le Chatelier principle again. So we count the total number of moles of gases. We have to look only at the gases on the left and on the right. 2 mole of gas plus 1 mole of gas, so 3 moles of gases. So a lot of students, they just know like, oh, they state 3 moles on the left and then 2 mole on the right. Should be 3 moles of gases on the left, 2 moles of gases on the right. So you think about the greater the number of moles of gases, the greater is the pressure exerted. So when you increase pressure, when pressure increases, the first thing the system will try and do is to oppose the change. So therefore the system will try to oppose the change. The system tries to decrease pressure. And how do you decrease pressure? You want to shift to the side with lesser gaseous molecules, and therefore you will shift to the right hand side because the right side has lesser number of gaseous molecules. That was what we had stated previously. And given that higher pressure will give you faster rate, higher pressure will give you a greater equilibrium yield because you shift it to the right hand side. But why do we not actually use higher pressure than 1 atmospheric pressure? When we do use 200 atmospheric pressure for Haber process, that is because even at 1 atmospheric pressure, which is what we use, the yield of SO3 is already acceptable and quite high. So it is actually the cost factor. It costs more. It costs a lot more to go to higher pressure. So the yield is already acceptable and it's expensive. It's expensive. So it's acceptable, it's already quite high. It is expensive to apply even higher pressure. When you already have good enough yield, you might as well, stick with it and be happy with it. Whereas in the Haber process, you really don't have an acceptable yield of NH3, and therefore you have to really increase the pressure to a much higher pressure. There's 200 atmospheric pressure for Haber process to produce ammonia. I think I've written more than enough there. In the third stage of the process, the sulfur dioxide is dissolved in this 98% sulfuric acid. So what you actually get is you get oleum. If you think about the equations, so the SO3 actually dissolve in concentrated sulfuric acid, and then you add them up, you get H2S2O7. That is what you call oleum. And then this H2S2O7 is what you dissolve in water to give you your concentrated sulfuric acid. And when you balance the equations, you will need 2 of that. So 4 hydrogen, 2 sulfur, and then 8 oxygen like that. So why in the world did we not just do it directly? Because we know that in the formation of acid rain is basically your rainwater. Your rainwater is H2O, and that SO3 that was produced by these catalyzed oxidations of SO2 reacting with NO2, giving you SO3 and NO again. Of course, the role of the NO2 is acting as a catalyst there, as the NO initially would have been produced, the NO2 would have been produced from NO oxidized by the oxygen in the air to give you NO2. This is what happened in the formation of acid rains. This is the catalytic cycle, giving you the SO3, not in a reversible step because you are in the atmospheric chemistry region. Okay, so that is H2SO4, and that is your acid rain. So you will see that in the formation of acid rain, this is directly done. But then in industry, this is man-made process. This is natural atmospheric formation of acid rain. We don't add the SO3 into water straight away in industry because it's actually very, very exothermic. So we are dealing with humans, human life in industry. So in terms of chemical engineering aspects, when something is very, very exothermic, it releases a lot of heat as well as and also corrosive H2SO4 fumes. So it is safer to go through via this oleum route, which is less exothermic, and therefore you maintain the safety inside that industrial process there. So write equations for the reaction of sulfur trioxide with sulfuric acid and for the subsequent reaction. So basically this is via the oleum. You don't really need to know the formula of oleum because you know that based on what I've done earlier. So oleum is basically you just sum up the whole thing, 2 hydrogen, 2 sulfur and 7 oxygen, and from there you can just add water to give you your sulfuric acid there. I've just added in the name oleum so that it sounds fancy, but it's actually part of your syllabus content even when you are doing the GCSE, IGCSE and O-level chemistry. Okay, so it had equations, so you're supposed to have 2 equations showing you the stepwise formation of the H2SO4 from SO3, not from the acid rain, but in the man-made process here. Whereas this was direct route because this is in the atmospheric chemistry, the formation of acid rain, the H2SO4 in acid rain there. Now this this part D question, this thing has been taken out from the syllabus if I'm not mistaken. So we use it as additive in some food and wines because this SO2 prevents, so it's an antioxidant. So it's an antioxidant. It prevents your food from getting oxidized. So it prevents food from being oxidized and going bad, rotting, okay, due to the oxygen in the air there. But if I'm not mistaken, this has already been phased out from the new syllabus, so you will no longer see it. But if you go back to like the 2015 Cambridge International Syllabus, you will have seen this particular statement and how it is being used as additive in foods and wine. Now question part E, we have a mole calculation question here. So the wine contains SO2. As it was mentioned, you add it as an additive in order to prevent the wine from getting oxidized, because wine has alcohol, and when the alcohol gets oxidized to carboxylic acid, your wine will no longer be having the alcohol content. It will just be sour, and you don't want to be drinking sour wine. Otherwise, you might as well just drink some vinegar, okay, like a apple cider vinegar or something like that. Anyway, how many moles of SO2 are present in 50 cm³ of the wine? So what do we have here? We are given information on the iodine, and the iodine will react with the SO2 in the wine. We want to know the mole of SO2 present in the wine. So we reacted 50 cm³ of the wine, which is the whole of that. So we find the information on the I2. We can see that the mole of the SO2 is to the mole of the I2. 1 mole of SO2 reacted with 1 mole of I2. Oops, sorry, not 2 at the bottom, but 1 at the bottom. 1 mole of SO2 reacted with 1 mole of I2 from the balance equation. You will know that I like this fraction method as I've done in all my topical playlists, in all the topical structure questions, topical multiple choice questions, in all my previous tutorials. I've done this fraction method. Then on the right hand side is my actual amount. I want the actual amount of the mole of SO2. At the bottom, I have the concentration, which is in mole per dm³. So N equal to CV. But the most common mistake really is people forget that cm³ have to be converted to dm³ in order for the unit to cancel out. So at the bottom, I have 0.010 mole per dm³. That's 12.35 times 10 to the minus 3, or divide by 1,000. I just move that up there, and I get the actual mole of the SO2 that's present in the wine. So 0.010 times 12.35 times 10 to the minus 3, I get 1.235 times 10 to the power minus 4 mole. Looking at the option here, I have 1, 2, 3, and 4 significant figure. This is 2 significant figure. This is 3 significant figure. This is 4 sig fig. I would say 3 to 4 sig fig 3 to 4 sig fig would have been acceptable in this question. I'll just leave it as the exact answer here because it is 4 sig fig within the range of these 12.35 cm³ there. So how many moles of SO2 are present in 1 dm³ of the wine? So if we have 50.0 cm³ of the wine and it has this much SO2 dissolved in it, so therefore if we have 1 dm³, which is 1000 cm³, so I cannot compare 1 dm³ straight away because the units are not the same. Now that the units are the same, I can do my direct proportion, because if you do the direct proportion correctly, the unit volume will cancel out. So 1000 cm³ divided by 50.0 cm³, and if you can follow the math and follow the unit, you will see the cm³ and the cm³ cancel. So that is a factor of 1000 divided by 50, so I get 2.47 times 10 to the power minus 3 mole. Let me just double check my calculation because I might have pressed it incorrectly just now. Yep, I get 2.47 times 10 to the power minus 3 mole. What's the next thing they want to sum up this question? They want how many milligrams of the SO2. Typically, we work in gram because mass over mR is in gram over gram per mole. What do they want? In the 1 dm³ of the wine. Give your answer to 3 significant figure. So basically they want the mass, okay? Without thinking about gram or milligram, they want the mass. They want the mass of SO2. So I have the mole of SO2. I want the mass. So realistically speaking, I need the mR of the SO2, and this is going to be 32.1 plus 16.0 times 2 from your periodic table. And I get 64.1 there. So what did I want? They want in 1 dm³ of the wine. So we know in 1 dm³ of the wine, there was this much mole. So if we have mole equal to mass over mR, so the mass will be in gram, you see, because the mR is, what is the mass in gram for 1 mole of the substance? So the mass there is going to be the mole times mR. So the mole is 2.47 times 10 to the power minus 3 mole. I multiply that by 64.1 gram per mole. The gram per mole and the mole will definitely cancel out. My point is your mass is in gram. So your previous answer times by 64.1 and I get 0.158327. This is in gram, but they want it in milligram. They even stated the answer here in milligram, and one gram is 1000 milligram. So I simply multiply that by 1000 milligram, and this is present in 1 gram. So the per gram and the gram cancel. Basically, I just need to multiply by 1000 and I get 158.327. This is now milligram. But again, they want it to 3 significant figure. So 1, 2, 3. I look at the 4th one, and this run up to 158 milligram of these sulfur dioxide in this 1 dm³ of wine there. So that's it really for this 18 mark really good question here.